Apes, and welcome back to our screencast series of Chapter 2, and this is the second screencast in this series. Okay, so we're going to continue with the idea of chemistry, and we're going to do that quick review. So we know that elements are the fundamental type of matter, and that an element is any type of chemical substance with a given set of properties. So, hydrogen, oxygen, nitrogen, sulfur, all of those are elements. Those are going to be the main ones that we're going to be considering, the ones that are actual pollutants. We'll talk about phosphorus as a mineral that we need, and that does not have an atmospheric state. Okay, so all of the elements, that's what we're going to be talking about. And we know that elements are made up of atoms. They're the smallest components of an element. They maintain an element's chemical properties. And I'm sure I don't even have to tell you that element is made up of subatomic particles. In the center, in the nucleus, are the protons and the neutrons. Protons are positively charged, neutrons are neutral in their charge, and they make up the atom's mass. And then surrounding that nucleus are the electrons, and the electrons are really, really tiny in comparison to the protons and the neutrons, and they're in constant motion. They're orbiting that nucleus in different energy levels, and that it's the valence electrons that are responsible for forming bonds, and electrons are negatively charged particles. I want to go back and also say that protons and neutrons make up, the number of protons, makes up the atomic number that we see on the periodic table. All of this should be a refresher, so I'm going through it really quickly with you. We've seen pictures similar to this before. Here's our nucleus. This happens to be nitrogen, and it has the atomic number of 7, so that means it's going to have 7 protons and 7 neutrons, and you can see it has 7 electrons here. Nothing that is new to you. You've seen this before, so I'm going to fly by this. We've talked about isotopes, so just a little bit of a refresher on isotopes. You've had this in chemistry. And these are atoms of the same element with different number of neutrons. You might have had carbon-14. If you had me in biology when we talked about isotopes, that's the example we used. And carbon-14 is a radioactive isotope because the nucleus is unstable with a greater number of neutrons. And because it's unstable, it causes it to wobble and leak radiation. And I always think of a ceiling fan that is out of balance and how it wobbles, and it expends extra energy because of that wobbling. So an isotope is going to react a little bit differently than a regular atom would, or regular element would, because it's going to be given off that energy source, usually radiation. So we talked about the mass number is the combined number of protons and neutrons, and when we think about bonding, we know that there's different kinds of bonding. There's covalent bonding and ionic bonding, hydrogen bonding and peptide bonding. We could kind of make a song out of it. But when we have covalent bonding, we're going to have a sharing of electrons, and when we have ionic bonding, we're going to have an exchange of electrons. And when that happens, when we exchange the electrons, it either gains or loses an electron, then they become known as an ion. So an anion is a negative ion that has gained an electron. And if you haven't learned the little way to remember that is, I think of the spelling, A-N-I-O-N, A as A, N as negative ion, okay, a negative ion, so that means it's going to gain an electron. And then a cation is the one that loses it, that's going to be positively charged. And I have 3 pet cats. You'll probably hear about all of them at some point. And they're positive. It's positive to have a cat. Sorry if you're not a cat lover. So that's a cation. So we know that we have these conditions that can happen within those elements. So here we go. This is the example of isotopes, and this is dealing with hydrogen. And hydrogen, doesn't have a neutron. If you know, hydrogen only has one proton and one electron. So if somehow in nature a neutron gets put in the nucleus with the hydrogen, it becomes an isotope. We also know that if this hydrogen loses the electron, it becomes a hydrogen ion, and sometimes hydrogen ions are referred to as protons or even photons. Okay, sometimes. Okay, just in case you hear that somewhere or see that written somewhere, and it's just a positively charged ion because it lost that electron. Okay, so let's talk about radioactive isotopes since I mentioned those. And there's some details that you need to know about radioactive isotopes. And they decay at a very constant rate because of their unstable nuclei that they have. Stable isotopes are non-radioactive. So there is like carbon-13, which is a stable radioactive, a stable isotope where it doesn't leak radiation. But then the unstable isotopes, they're going to be the ones like carbon-14 that leak radiation. They emit high energy of radiation. And this radiation is going to be referred to as an ionizing radiation because it generates ions when it strikes other atoms. So what does that mean to you? If it generates ions, do you think it causes a transfer of those electrons? I hope that's the way that you're thinking from your experience. And these are the kind of things that you need to be able to put together when you're doing the exam. So isotopes have what they call a half-life, and this is the amount of time it takes for 1/2 of the atoms to give off radiation and decay. And as I said, typically those half-lives, that rate is constant over time. So when we think about different radioactive isotopes like uranium and plutonium, they have different half-lives, and that can range from fractions of a second, where it's over in a second, to billions of years. And that's where it comes concerning when we have radiation leaks from nuclear power plants like the one in Tohoku, Japan, because that type of radiation is the type that lasts billions of years. It takes billions of years to decay. So let's take a look. Uranium-235 is one of the radiations that has commercial use in the nuclear power plants, and it has a half-life of 700 million years. It takes 700 million years for half of its atoms to decay and give off radiation. So when we think that power plant had a leak and we think, oh, we're going to clean this radiation up, then we're going to move on, it's going to be staying there for a very long time. Chernobyl back in the 80s had a huge radiation leak. They'd give tours of Chernobyl. You're not allowed to step on the ground. You have to stay within the buses. They kind of drive you around and they show the place. But people had gotten cancer, birth defects, miscarriages. A lot of problems have happened. Brain damage, mental impairments have happened because of it, and they can't go back on that land. So that's one of the reasons why it's so important for nuclear power that we learn how to contain it and protect it so that we can use it. That's why it's so dangerous. So when we talk about molecules, okay, refresher on this, it's a combination of two or more atoms, just in case you forgot. So even when we write O2, and I don't know where my little arrow is, there it is, even though we write O2, that is a molecule, as well as H2O is a molecule of water, and C6H12O6 is a molecule of glucose. It's a single molecule. A compound is when we take these molecules and we put two or more different elements together. So when I was saying to you water, H2O, and one molecule of water, I'm just going to write H2O. Two molecules, I would put 2H2O. Three molecules, I would be 3H2O. But that H2O also tells me it's a compound. And as you know, it's kind of like a list of ingredients. It tells me exactly how many hydrogens I'm going to need and how many oxygens I'm going to need to make up that water molecule. The same thing is true with the glucose I mentioned. It's a list of ingredients. C6H12O6 tells me I need 6 carbons, I need 12 hydrogens, and I need 6 oxygens in order to make that glucose. Okay, so we see water here. There's no number before that, so that tells me that I have one molecule of water. If I put a number in front of it, I have 2 molecules of water. The same thing with carbon dioxide. Tells me I need carbon and 2 oxygen in order to make it. If I do 5, I have 5 molecules of carbon dioxide. So just by putting that number in front. And then, as you all remember, that also tells you when you have the number of molecules, that's also telling you, and I'll focus on carbon, that or carbon dioxide, that we need 5 carbons and we need 10 oxygens, or that's what we're going to have in those 5 molecules of carbon dioxide. Okay, so just a little quick refresher there. Atoms bond because of their attraction for each other's electrons. Remember the octet rule of 8. They want to have 8 valence electrons if they can to be stable, or they want their electrons to be paired. So we know that the way that electrons bond, some can be shared equally, and that's going to be called covalent bonding. We know that atoms may share electrons unequally. We know that water is a polar molecule because the oxygen side has more electrons than the hydrogen side, and that enables water to be able to attract other water molecules and form cohesion. So cohesive forces, you remember that. It's adhesion when it's with different substances. And if you're not sure about those two, please go back and check them. We know that ionic compounds, they are going to transfer electrons. And you might remember I gave the example in general biology, and I'm sure Mrs. Mitchell did as well, that table salt, if you think of sodium, it's a silvery metal that's explosive in water. Those are its properties. And chlorine is a greenish poisonous gas. Neither one sound very appetizing, but when they bond ionically and they transfer the electrons, sodium loses that electron, chlorine gains it, it forms table salt, something that you season your food with and you use regularly. We also know through our understanding of compounds and atoms and elements that solutions can form. We can mix compounds together and we can make solutions or suspensions. And a solution is a mixture of substances that have no chemical bonding. So air, we've got particles in the air that are not bonding together. The ocean water, the salt doesn't bond with the ocean water. It's carried by the molecules so that it's evenly distributed. We've talked about salt and pepper when you mix those together. Those are some examples. Petroleum, ozone, all of those are considered solutions, and you might not have known that. We're coming to the end of our time. We will continue in the next screencast.